This video is for the beginning of Chapter 2 of the textbook Conceptual Dynamics. And this is basically the first main topic of the course, and it's called rectilinear motion. So if you recall, there were two different ways that we could model a body. We could model it as a rigid body or as a particle. So when we considered it a rigid body, it had size as well as mass. And so not only did we have to consider its translation, but we also had to consider its rotation. And so considering that, the motion can get quite complex. So the object can move in the x, the y, and the z. So that's 3 dimensions, that's 3 degrees of freedom. But then it can also rotate about each of those axes. And so altogether, that's 6 degrees of freedom. In order to simplify things, we will start in this course with just a particle model. And so that is, we will treat our systems as if they're just a point, and then we don't have to consider their rotation, just their translation. And so that brings the complexity down, so we only have to consider 3 degrees of freedom movement in the x, y, and z translation. But we're going to make it even simpler than that, and we're going to constrain our particle to just move along a straight line, to move in one dimension, and we will call that rectilinear motion. And so this is the picture. So we have our straight line, and our particle can move back and forth, but it's constrained to move on that line. In this case, we're calling that axis, that line, S. And so in this section, in this video, we're going to introduce some important terminology, specifically for the case of rectilinear motion, but it's terminology that we're going to use throughout the course. And so the terminology, the definitions, are things that you're quite familiar with. So you've learned about it in physics and things like that, but you also use it in your everyday life. And so the first concept is the notion of position. And so everybody understands what position is. And if I asked you to describe it or explain what that is, you might say, it's where something is, it's where something's located. And so if I said, where do you live? I might say, I live 45 miles southwest of Detroit. And so the thing that was important there, or one of the things that was important, was I told you where I was in reference to something else. I told you I was southwest of Detroit. And so when we talk about position, we want to do the same thing. We want to have a reference. We want to have sort of a zero. And so when we define position, it's where we are located in some coordinate system relative to some origin. And so in this case, our system, our coordinate system, it's kind of like a number line. It's this s-axis. And so the question is, where am I relative to the origin of this coordinate system? Where am I relative to the zero of the number line? Am I 4 units to the right? Am I 2 units to the left? That's how we sort of talk. In this case, position is a vector. Position has magnitude and direction. When I told you where I lived, I said I'm 45 miles southwest of Detroit. So the 45 miles is the magnitude, the southwest is the direction. For these rectilinear motion case, position is still a vector, but we're going to write it as if it were a scalar. And we're not going to use bold. We're not going to put an over bar. It's written just as a S, like a scalar. And so the way that we are going to indicate direction in this case is with sign. So if it's positive 6, it's 6 units to the right. That's the direction. If it's negative 6, it's 6 units to the left. Another important concept is displacement, and displacement is related to position, but it's different than position. So position is an absolute sort of concept. Where am I relative to the origin? Displacement is a change. It is the difference between where I ended up and where I started. And so in this case, maybe I started at 3 units and I ended up at 6 units. And so my displacement was 6 minus 3 is 3 units. So my displacement was 3 units to the right because it was positive. So the positive indicated the direction. And so, displacement, that sort of makes sense. The interesting thing about displacement is that it doesn't matter how we moved. It doesn't matter the path we took from our initial position to our final position. So it doesn't matter if I went past my final position and came back. It doesn't matter if I went backwards first and then came forward. With displacement, all that matters is the initial position and the final position. It doesn't matter what you did in between. There is a quantity, which we'll call the total distance traveled, which does depend on the path taken. And so in this case, let's say that I started here at this position. Let's say that was 4 units, and I ended up at 2 units. And so if I subtract my final position from my initial position, 2 minus 4, my displacement was minus 2. So my displacement was 2 units to the left of where I started, because the negative sign indicates to the left. The distance traveled, however, does depend on how I moved. So in this case, let's say I started at 4, I went up to 10, and then I went back to 2. And so in that case, I moved forward 6 units, and then I moved backwards 8 units. And so my total distance traveled was 6 plus 8, which is 14. And so in that case, it did matter the path that I took. Here, total distance traveled is a scalar. I don't say I traveled 14 units to the right or 14 units to the left or southwest or whatever. I just said I traveled a total distance of 14 units. It has a magnitude, but no direction. And so now I have a question. When are displacement and total distance traveled the same? So go ahead and take a second to think about that. Okay, so there's 2 things that matter. So one thing that matters is that we cannot have our particle turn around. So if we turn around, then we have legs in one direction and legs in another direction. So if we move in one direction without turning around, then we'll have the same magnitude. So if I started at 4 and I went to 10, displacement was 6, and the total distance traveled was 6. The other thing that we have to be a little bit careful about, so not only is there no turns, but also it has to be in the positive direction. It has to be forward, because displacement is a vector and total distance traveled is not. So if I traveled 6 units to the left, my displacement would be -6, but my total distance traveled would be +6. So if I move forward without turning around, then the total distance traveled and the displacement will be equal. That's not really, that isn't important. This was just an example to try and distinguish the difference between those 2 concepts. Another important concept is the notion of velocity. And so again, this is a number, or this is a word or a definition that we use all the time. And so if I asked you to tell me what does velocity mean, you might tell me it's how fast something moves. And so how fast something moves, what does that mean? Well, one way to think about that is it's sort of how much ground am I covering and how quickly am I covering ground? So if I'm moving a lot in a certain unit of time, then I have a high velocity. If I'm not covering very much ground, or my position is changing slowly, then my velocity is smaller. To be sort of more precise, we will say that velocity is the time rate of change of position. So in this case, it's how much does my position change for a given unit of time. To be a little bit careful, we have to distinguish that this is actually the average velocity. So if I sort of said my delta was 30 miles over an hour, if I said it, I live 30 miles from work and it took me 1 hour to get home, then you would sort of say my average velocity was 30 miles per hour. That's how much that's how much my position changed for a given unit of time. At any given instant of time, my velocity would not be 30 miles per hour. I stopped at a stop sign, so my velocity was 0. And then I sped up to pass some slow person on the drive, and I sped up to 45 miles per hour. And so at any given instant, my velocity could have been different, but on average, over that entire hour, on average, I was going 30 miles per hour. If I want the instantaneous velocity, if I want the velocity at any specific instant, um, we have to use what's called the derivative. And the way to think about that is that our time delta, our time difference, is becoming very small. And when that time difference becomes infinitesimally small, that's when we get a derivative. And you'll notice here um, that we use this dot notation. So this is shorthand. We will use that to mean the derivative of s with respect to time. Again, velocity is a vector. I could say I'm 45 miles per hour in the southwest direction. With rectilinear motion, we will use sign to indicate direction. So if the velocity is positive, that means I'm moving to the right. If my velocity is negative, that means I'm moving to the left. And then speed, people kind of use the word speed interchangeably with velocity. But to be more precise, speed is the magnitude of our velocity. So if my velocity is 45 miles per hour southwest, my speed is just 45 miles per hour. It's just the magnitude of my velocity. It's not the direction. So here we're going to do a little example to try to give us a better sense of what velocity is. And so here we have these sort of snapshots of this ball rolling. Each snapshot is an equal amount of time after the preceding snapshot. So, this first snapshot was maybe time equals 0 seconds. This next was at time equals 1 second, time equals 2 seconds, time equals 3 seconds. So each snapshot is a same amount of time after the preceding one. And so here, I want you to look at each of these, and I want you to rank the velocity of each of the pictures. And so, the starting velocity. And so, since we sort of only have these snapshots, we can really only talk about average velocity between the first two time instances. If I just look at this picture of a ball, I can't tell how fast it's going. But if I know that its position is here at the first snapshot, and then its position is here at the second snapshot, then I know how far it traveled. I know the delta S in that delta T time. So I can kind of gauge what the average velocity was between those time instances, even if I don't necessarily know what it was doing in between the two snapshots. So go ahead and think about that problem. So if I look at this, velocity is how fast the position is changing with respect to time. How much did my position change for a given instant of time? And if I look at these pictures, A and C, it sort of looks like my ball covers the same displacement, covers the same distance for the same delta T. So A and C look like they have about the same average initial velocity. With B and D, similar. It looks like the amount of ground covered between the first two snapshots for the B and D case also look about the same. But comparing the two, B and D cover much more ground than A and C. And so that means that B and D have a higher velocity and A and C have a lower velocity. And so I would say B and D have the highest initial and A and C have the lowest. Another example, which of these pictures have constant velocity, or represent a case where the ball has constant velocity. So go ahead and think about that for a second. Okay, so again, velocity is how much ground, how much our position is changing for a given change in time. And so in this case, A looks like it's covering the same amount of ground each time snap. So same delta S in the first snapshot, same delta S between the next two snapshots. And so A, I would say, has a constant velocity. Same thing with D. The amount of position change is the same for each snapshot. So I would say A and D are constant, but B and C are not. You can see that the delta S is changing as the ball rolls in each of these cases. And so in each of those cases, the velocity is changing. So here's another example. And so here we have a car driving along a straight line, and the car's position is changing. And so looking at this picture, so this is our position S versus time. And so the graph is a curve, but the car itself is not going around a curve. The car is going in a straight line. Okay, it's S is where our position is on our number line. So that can be a little bit challenging to wrap your head around, and so try to think about it that way. And so the question is, looking at that graph, is A, our car speeding up? Is it B, slowing down? Is it C, does it speed up and then slow down? Or D, does it move with constant velocity? So go ahead and try to think about that for a second. All right, so if we look at it initially, this is its position at some instant of time, and then let's look, some instant of, so at time equals 0, that's our position, and then let's say at time equals 1, we have some other position. And so you can see it covered the position changed. So like at time equals 0, let's say it was at 5, and then at time equals 1, let's say it was at 7. So between those first two time instances, it covered 2 units, let's say. But let's look out here. So here's some other time instant and then an equal amount of time later. So here maybe it's at 9.5 and then here it's at 9.6. So at that time instant, its position is 9.5 and then an equal amount of time later, it's at 9.6. And so you can see initially between a certain delta t, it covered a lot more position. Its position changed on the number line a lot more than it did between two time instances down here. And that's sort of the trend. It's covering, its position is changing, its S is changing less as time progresses. And so that means that the car is slowing down. It's covering less ground over each instant of time. The other way to think of that, velocity is delta S over delta T. So in this case, S is the Y and the delta T is the X. And so we can think of the delta S and the delta T as rise over run. So we can think of velocity as being the slope of this S versus T graph, of this position versus time graph. And so if we look, the slope initially is something like that, and then the slope becomes progressively smaller, progressively flatter as time progresses. And so the fact that the slope is going down, the slope is getting smaller, that indicates that the car is slowing down. Okay. Last concept, acceleration. So So again, if I asked you what does acceleration mean, that's a word that we use a lot. You might say something like, it's how quickly I'm speeding up, or it's how quickly I'm slowing down. And so more precisely, it's basically how our velocity is changing. So acceleration is the time rate of change of velocity. So how much does the velocity change for a given unit of time? Again, if I'm using a finite period of time, an hour or whatever, then what I'm talking about is the average velocity. And if I want the instantaneous velocity, then I need to use a derivative. And so acceleration is the first derivative of velocity. We know that velocity is also the derivative of position. And so acceleration is also the second derivative of position, where again, we use this dot notation. And if we think about what are the units of acceleration, so velocity is position with respect to time. So you can imagine units of position over units of time. So velocity might be something like a meter per second. That would be velocity. Acceleration is velocity per time. So it might be something like a meter per second per second. And so a meter per second, you can also say that as meter per second squared. So it's distance per unit time squared. And a way to think about that, meter per second, dividing by something is the same as multiplying by its reciprocal. So dividing by s is the same as multiplying by 1 over s. And so again, here we have our sort of our snapshot pictures to try to, again, sort of wrap our heads around what acceleration is. So looking at these snapshots, take a second and think about which case has positive acceleration, which case has negative acceleration, and which case has zero acceleration. Okay, so if we look at this, for example, A. So each snapshot, the ball travels the same distance. And so since velocity is delta s over delta t, the velocity is constant. I'm covering the same amount of ground for the same amount of time. So if my velocity is constant, then and acceleration is how my velocity is changing, then the acceleration must be zero. So acceleration is delta v over delta t. In the case of A, delta v is zero. The velocity, there is no change in velocity. Same thing with D, also zero acceleration. If we look at B, the distance that we're covering gets smaller. So this delta s is much bigger than this delta s. And so again, since velocity is delta s over delta t, that means velocity is decreasing. And then acceleration is how the velocity is changing. It's delta v over delta t. If v is getting smaller, that means delta v is negative, and that means the acceleration of b is negative. We're slowing down. Our velocity is decreasing. If we look at c, the distance covered is increasing, and so in that case, our velocity is increasing, and so our acceleration must be positive. So that brings us to the end of this video. So we introduced the simplest type of motion that we're going to analyze in this class, where we're dealing with a particle constrained to move along a line, just backwards and forwards. We then introduced formally some different sort of concepts, some different definitions that we're going to use a lot in this class. So we looked at position. What does that mean? What does it mean as compared to displacement, as compared to distance traveled? We talked about time rate of change. So velocity is a time rate of change, acceleration is a time rate of change. And what does it mean for an average versus an instantaneous? We then talked about what velocity is, what speed is, and what acceleration is.